carbon dioxide, R744, CO2 are all names for the same substance. In this video, produced by Danfoss, we will refer to this as CO2 only. The video shows the different phases of CO2 and how two of the phase changes occur by altering either the pressure or the temperature. When compared with commonly used refrigerants R134A and R717, CO2 has some unique characteristics. It operates at a much higher pressure, but across a narrower temperature range than both the R134A and R717. The pressure at the triple point is high, and the temperature at the critical point is low. These facts must be taken into account when CO2 is utilized as a refrigerant. The application of CO2 as a refrigerant was introduced in 1850. From studying the literature, it can be established that CO2 refrigerant systems were developed during the following years and that they were at their peak in the 1920s and early 1930s. Between 1950 and 1960, CO2 refrigeration technology virtually disappeared from the market. However, in 1993, this CO2 refrigeration technology was revived. In order to observe the CO2 phase changes, an observation cell, specially designed and constructed by Danfoss, has been used. The cell is designed to withstand pressures up to 140 bar gauge. In this diagram, the coloured areas define the temperature and pressure limits at which the CO2 vapour, liquid, solid and supercritical phases exist. This is known as the temperature pressure diagram or phase diagram for pure CO2. The red solid lines indicate the pressure and corresponding temperatures at which two different phases of CO2 exist in equilibrium. For example, liquid and vapour, solid and vapour, and solid and liquid. Here is the triple point, and here is the critical point on the phase diagram. For refrigeration purposes, the pressure enthalpy diagram is commonly used. For CO2 applications, this diagram has to be extended so that the solid and supercritical phases are included. The coloured areas indicate the different phases of CO2, namely vapour, liquid, solid and supercritical. The triple point is here, the critical point is here. We would now like to define the triple point, and in the first sequence the CO2 is cooled by forced evaporation to the stage where it passes through the triple point. The cell is charged with liquid CO2 at an ambient temperature of 20 degrees C, which has an equivalent pressure of 57.2 bar absolute. Venting CO2 from the vapour phase allows more liquid CO2 to decant from the supply cylinder to the cell, thus raising the liquid level. When the cell is sufficiently full, both the vent and charging valves are closed. When the CO2 content within the cell has settled, the vapour and liquid are in equilibrium. This is represented by the cross on the vapour-liquid line. The vent valve is now opened to release CO2 vapour. The pressure and therefore the temperature of the liquid CO2 falls rapidly as it boils to produce more vapour. The triple point is reached with further reduction in pressure and temperature. The system has now moved further down the vapor-liquid equilibrium line. Solid CO2 begins to form once a pressure of 5.2 bar absolute and a temperature of minus 56.6 degrees C has been reached. The triple point is the only pressure and temperature combination at which solid, liquid and vapor CO2 can exist simultaneously in equilibrium. As the pressure continues to fall below the triple point, only solid and vapor are present in the cell. Solid CO2 is also known as dry ice. It has a surface temperature of minus 78.4 degrees C at standard atmospheric temperature pressure. The pressure inside the cell is now approximately equal to the surrounding atmosphere of 1 bar absolute. The vent valve is closed. The entire cell is now below ambient temperature and will absorb heat from the surroundings. Triple point conditions are re-established as the solid CO2 melts, and as the pressure and temperature rises, the cell contains liquid CO2 and vapor in equilibrium. We would now like to define the supercritical phase, and in the next sequence the CO2 will be heated to increase its temperature and pressure to the stage where it passes through its critical point into the supercritical phase. The critical point is the pressure and temperature combination at which the density of both the liquid and vapor are equal. The distinction between the liquid and vapor phases disappears gradually as the pressure and temperature increases towards the critical point, until only a single phase exists in the supercritical area. The density of CO2 at the critical point is 468 kilograms per meter cubed, which is of the same order as many liquids, but is nearly 2.5 times higher than the CO2 vapor density at the starting point of 20 degrees C. The cell is again filled with liquid CO2 under the same conditions as before. The temperature of the liquid CO2 increases with a consequent increase in pressure as the liquid CO2 boils. The CO2 vapor density above the liquid increases as the temperature and the pressure increase, and the distinction between the two phases disappears. CO2 now exists at a pressure of 73.6 bar absolute and a temperature of 31 degrees C. After a further small increase in temperature, all the CO2 present in the cell is now in the supercritical phase. This supercritical CO2 has some interesting and user-friendly properties. Its high density gives it some of the properties of a liquid, so for example it can act as a solvent for extracting various materials. However, its viscosity is much lower than for most liquids, and its diffusivity is consequently higher. These properties have led to a great deal of interest in the use of supercritical CO2 as a safe, effective solvent, in particular for food products. Cell heating is isolated. The supercritical CO2 pressure is reduced by opening the vent valve, and the CO2 temperature decreases simultaneously. When the critical point is reached, the distinction between the liquid and vapour phases becomes evident again. Pressure above the liquid CO2 is further reduced in stages by venting more vapour from the cell, and once again the cell contains liquid and vapour in equilibrium. We trust that you have found this short Danfoss video to be of interest and would thank you for your attention. For further information, please contact your local Danfoss sales organisation.